Thanks very much. And yeah, also I would like to start with thanking Simon and Adil for this organizing this workshop and this program. It's really great, and I really enjoyed it. And also thanks for the hospitality we had. And yeah, so but also something maybe came out of this this workshop. So it was very good that Gareth talked ahead of mine and presenting some more complicated equations already. And I will kind of follow up on this and show to some extent how to solve these equations numerically. So it's especially related to the first part of Gareth's talk. And I call this fluid deformable surfaces. Other people do this as well, pointing out that we are considering things which have some solid fluid duality, and just well, to motivate this a bit more, so we are interested in like thin sheets of soft materials with this property. So this materials can store elastic energy when stretched or bent, like solid shells, and here an extreme example. And but in addition to that, so under in-plane shear, they flow as viscous two-dimensional fluids. And there's another extreme example of that. And this type of materials one can find, or one in biological membranes, or at least some model membranes we will consider. So in the context what Gareth talked on, but with some further approximations, maybe these are also good models to describe the cellular cortex with some active component or epithelial tissue. Okay, so so these are surfaces which evolve, and they are fluid and they deform and so on. But typically, such in these applications, they are not isolated. So there are some fluid inside, outside, whatsoever. However, we would like to focus only on this interface, on this surface, and one can nicely decouple this from what happens in the bulk phases. If well, the viscosity of my surface is larger than the viscosity in the bulk phases, and there is this well, Subman-Delbrück hydrodynamic length, which relates the two viscosities to each other. And if this is large, then it's fair to decouple this. So this allows us to well, only consider this evolving surfaces, and well, mathematically, well, they change shape. This is mainly governed by well, geometric properties and well, some quantity we define on the surface, or some PDE on this surface. It's a coupled system. Okay, well, I promised complicated equations, so let's start with the model we would like to solve. So it's an incompressible surface Navier-Stokes equation with bending terms and constrained enclosed volume. So we have a closed surface, and the volume inside should be fixed. And it's incompressible, essentially meaning that also the area is fixed, and it's also locally fixed. And so it's a Navier-Stokes equation, and well, it looks kind of similar to maybe Navier-Stokes equation in 2D and 3D we are familiar with. So we have a velocity, we have a pressure. However, now our velocity is defined only on this surface. But still, we use here the coordinates of the embedding space. So it's still x, y, z. And then we have this well, convective term with some material velocity. I will come to that. Then we have a rate of deformation tensor. We have a Reynolds number. So the only difference, and we have this inextensibility constraint. So the only difference are essentially the operators. These are now operators defined on the curved space. So for scalar quantities like here, so that's the surface gradient, covariant derivative, if you like. For vector quantities, one has to think a bit more. So there's not only one operator, there are various. And here, what we take is the surface gradient defined in this form. So it's a projection of my velocity to the tangent plane, and then the covariant derivative. But in addition, we also take into account the normal component of our velocity, and B here is the shape operator. Okay, and the divergence is the dual of this in this form. Okay, so these are differences. In addition, well, there's this term which couples the pressure and the mean curvature and the normal. This is something one gets from deriving this equation as a thin film limit from 3D Navier-Stokes. And then there's some forcing term, B. So this comes from my bending energy. So that's essentially the variation derivative of this Helfrich energy, neglecting Gaussian curvature contributions. With BE, the bending capillary number, so related to the bending rigidity. And then we have this term with the Lagrange multiplier. This is used to enforce this volume constraint encoded here. So that's the model we would like to solve. And okay, that's before we're going to do this, let's simplify this a bit and analyze it a bit more. So let's drop this bending and the enclosed volume, and then it's the surface Navier-Stokes, incompressible surface Navier-Stokes equations. Essentially goes back to Scribben, where this was used as a boundary condition in two-phase flow. And then there are various derivations of this type of equation, different methods like thin film limit from 3D Navier-Stokes, or mass and momentum conservation in an intrinsic or an extrinsic formulation, and so on. And in this very last one, all they are compared and related to each other, and indeed, and this notation, they all lead to this form. Okay, now one nice way to understand what's going on is to decompose this velocity into a tangential component and a normal component. So nu is the normal, that's the normal velocity. Okay, so plugging this in there and then grouping terms, we can write this as a coupled system for the tangential velocity and the normal velocity. And now there are many terms, and we have this new Bochner-Laplace here and the Gaussian curvature and so on, but I don't want to go into the details of all this, but what we nicely see is that there's strong coupling between the normal velocity and the tangential velocity. Well, especially here in this incompressibility constraint, we see that this is not zero, but it's compensated by the normal velocity and the mean curvature. And there are various other terms. So the normal velocity is in this equation, and the tangential velocity is in that equation. So at the end, any tangential flow induces shape deformation and vice versa. Right? So that's going to be essential. And now some words on the numerics. So we start with even this equation is maybe too complicated to do some analysis and some decent benchmarking. Let's further simplify it and say, well, it's just a stationary surface, so no known normal velocity, and we also go to the Stokes limit. And then we can compare two established methods for solving vector valued PDEs on surfaces. So we use surface finite elements, and we also compare two methods. So the first really works in this velocity pressure variables, and it uses a Taylor-Hood discretization. and the second reformulates our problem into a stream function vorticity formulation. So at the end, we only have scalar quantities and can solve that. And so we set up some surface mesh, such a bicconcave shape, and specify some force so that we induce some flow. And then, well, the essential idea for the numerical approach for this thing is to say, well, even if my flow now is tangential, I still keep the three components of the embedding space and penalize everything which is normal. So this is essentially this term, which we add. So all normal components to the velocity are penalized by some penalization. And now for this system, one can do actually numerical analysis, and one can show that, well, within this penalization, one needs a better approximation of the normal than the approximation for the velocity, or in this order to get convergence. And we looked at convergence properties for different quantities and got optimal order of convergence. So with this understanding for this simplified problem, we can now move on and go back to our original problem. And so we had, now this constraint and the bending. Okay, there for solving this bending terms, there's various theory available in terms of like solving just the Wilmer flow or the average problem. There's also some work done how this mesh should be treated if it's evolving and so on. So we use some mesh regularization, which here is based. So X is the parametrization of the surface. There is this geometric quantity that's the Laplace-Beltrami of this parametrization. Each component is related to the curvature. What is the curvature tensor? And so we use this as which gives us some freedom to move our grid points in tangential direction to get some optimal thing. And then, well, this gives us the material velocity, which is our velocity, and this mesh change. And well, that's the system. And well, we consider in each time step all geometric quantities explicit. So the normal is from the old time step, and the shape operator as well. And we consider as unknown not the new parametrization, but some surface uptake. Okay. And then in the first step, we say that our Lagrange multiplier is given. We don't deal with that too much. And then we solve our system for the unknowns, the velocity, pressure, mean curvature, and the surface uptake by solving this equation. And then in the next step, we have to deal with lambda, our Lagrange multiplier. So this is some nonlinear equation we have to solve by some iteration, and then we couple this, and this gives us the solution for the next time step. Okay. But now we can first look at some phenomena which occur here. So first of all, we forget about this volume conservation. So we start with a sphere and prescribed rotating velocity field on it. So now, as I said, each tangential flow induces normal flow, so shape deformation. So what happens is that the surface deforms and energy dissipates by this, and it converges to some state where, well, it's not a sphere anymore. So what is color coded here is the mean curvature, and it has a persistent rotation where kind of these bending forces and this centrifugal forces are balanced. Okay, And we can look at this, well, the kinetic energy goes down and somehow oscillates, and the Helfrich energy goes up and then also oscillates. Well, the Helfrich energy was here in minimum. But now this is kind of the final state we get. It's independent what we get on the Reynolds number. The dynamics depends on that, but not the final state. But it of course depends on the bending capillary number. So with larger bending numbers, well, it's stronger deformed. Okay. Now we can come up with some, well, semi-analytic description of this. Yep.
Can I just ask? You've already gone to Stokes flow?
No, it's Navier-Stokes here.
So you're getting the oscillations?
Yeah, the oscillations come from the inertia effects. Yeah. And right. So the black curve, well, it's still not Stokes, but it's very low Reynolds number. That's kind of related. Yeah. And so we can compare this with assuming axial symmetry here, and we can end up with some system of ODEs for this state, and like can compare what we want. And the nice thing, we can do a convergence study and find the same convergence orders we analyzed for our Stokes problem on the stationary surface. So it's assumed to be optimal what we get. Okay. Now, if we do the opposite thing, so we start with zero tangential flow, but some perturbed surface, and let this evolve. So as I said, well, due to the Helfrich energy, now this deforms. This deformation induces tangential flow and so on. So we can maybe first look at this for very low Reynolds numbers. So similar to what you probably get from Stokes flow. Then it deforms, induces this flow, and leads to, well, such a biconcave shape. And the energy curve for the Helfrich energy would be related to this black curve. So it's basically going stuck on this energy state. However, if we increase the Reynolds number, well, then we kind of go through this state more or less, but it further deforms and goes to this dumbbell shape. And this dumbbell shape has a lower energy. So kind of the flow helps to find the minimal energy shape for such a surface. Right? Okay. And well, we can do also some convergence studies here for the full problem for different arrows. The energy and the Helfrich energy and the area conservation and volume conservation. And also here we get essentially this optimal order of convergence.
Can you just illustrate? So you're saying these shapes are stabilized by the existence of the flow?
No, but what I'm saying, it's converging to a state, and this state is has zero tangential velocity, and it's equivalent with the equilibrium state for the Helfrich energy related to this reduced volume, so the relation between volume and area. What I only say is that the flow influences the dynamics, and it helps you to go through this meta-stable state here and find the equilibrium configuration. Okay. Okay. Now we can do this also for more complicated surfaces like this bunny, and that deforms and uses this flow and does something. And well, before this goes to an end, maybe have a look at the mesh. So this really strongly deforms, but in this region, but stays within some acceptable quality to do this. And at the end, this also goes to this such a biconcave shape with zero tangential velocity. Okay. Well, it's nice, so we can look at it twice, I guess. Okay. Good. So now we could ask the question about this. I started with was this sphere. We let it warp, and then it was going to some ellipsoidal shape with a persistent rotational state, right? And the question is, are these states stable? And and we looked at this, and well, under the assumption that everything is rotational symmetric, then these states are stable, and they are also reachable if you start from a rotational symmetric configuration. However, if you don't have this constraint, then well, any perturbation, so what we have here is a so-called killing vector field, and any perturbation of the shape or the flow field will lead to dissipation in energy. And that deforms the whole thing. And that's essentially what we see here. So out of this, this over time deforms and leads to, well, a shape which is rotating in the around another axis, and actually the energy of this is lower than the energy of that. So there are twists on that. So any perturbation of the shape or the velocity will lead to dissipation and form the new equilibrium shape or quasi-equilibrium shape. But any perturbation of this will probably also destroy this. So also this probably is not stable and evolve further to a state where there's zero tangential flow, and it's equivalent to this Seifert type equilibrium shapes. So the same happens here. So if you would start with such a oblate thing, also or this in a rotational symmetric setting would be stable, but if you get rid of this constraint, then any perturbation deforms this and also leads to this state and then further deforms. Okay, now what happens if we add some activity? And well, that's kind of the things we started here by discussing this with Gerrit, and so essentially that's the model he introduced to you, except that well, he looked at the Stokes approximation of this, but the essential part was this active forcing part, and well, he motivated various ways of how this this stress tensor should look like, and there are essentially two different things: some even and odd stress, and we looked here at the two simple things, so the isotropic things. And the question is, what happens if one adds such active stress? And this is now some really preliminary work. So we start with some perturbed sphere with zero tangential velocity at the beginning, and then well, due to this gradient in curvature, we have this forces, and that induces flow, and it deforms, and so on. And with this initial perturbation, it goes to such an oblate shape with the rotating flow, well, in that direction. And according to Gerrit, it's the right direction one should expect. Okay, so now if we start with a different perturbation, everything else is the same, then that deforms to something else. It goes after a while to such a dumbbell shape. And if we look at the rotational flow on this, then it's rotating here in that direction, there in that direction. Also, this is the right thing to expect. So this is nice. One can do this in looking at the dynamics here as well. Oops. And so here this is done in a bit more systematic way. So it's always the same reduced volume. So the same relation between volume and surface area, but different initial shapes. Like this, that. And the same forcing, and the question is how does it evolve? And these are some intermediate states, and these are the configurations at the end we get. So these are the equilibrium configurations, same as this Seifert equilibrium states, but with a persistent rotational flow. And the energy between this and that, this is different. So this has a lower energy, and that has the higher energy. So with this active chiral flows, one can kind of stabilize this equilibrium shape, but has a persistent rotating flow on it. So that's some first result. If this also leads to instabilities of the shape, we are still investigating. Okay. Now we can further complicate our model. So far we had only like one phase on the surface. We can have two different phases. Don't have to specify too much what these two different phases could be, or in the terms of like biomembranes or lipid membranes could be lipid ordered and lipid disordered phase, for example. So the question is now how to derive a system of equation where the shape evolves, we have flow on the surface, and we have different phases on the surface which also evolve in time. So there are different energy dissipation mechanisms which intertwine. And we use the Lagrange d'Alembert principle to derive this. And the idea, I briefly sketched this here, we start with our energies. So we have kind of Cahn-Hilliard type energy for an order parameter distinguishing the two different phases on the surface. We have this bending energy, where the bending rigidity and the spontaneous curvature now depends on the phase. And we have the kinetic energy. Okay. And then we have different dissipation mechanisms. Well, one is by our fluid, so that's our rate of strain tensor. We have friction, and we have dissipation due to this phase change. Right. So we have a dissipation potential, we have our energy, and we can define an Lagrangian. Then we have in addition some constraint that our flow should be inextensible. And then putting this all together, we end up with a system of equations for all our unknowns, which is thermodynamically consistent by construction. Okay, it looks like this. Let's go through this. So the first equation, so it's all defined on this evolving surface. The first equation for phi is kind of this Cahn-Hilliard equation, but now with convection, so we have a convective term, and our chemical potential, well, it's this part which comes from the Cahn-Hilliard energy, is this part which comes from the bending energy due to this dependency of the parameters on it. And then we have our flow equation, so our Navier-Stokes equation, but now it's a two-phase flow problem. But we have different same density and also the same viscosity for both phases here in the moment. So that looks like what we had before, now with some friction term and this bending term. This is now a bit more complicated due to all these dependencies. And it also has a tangential term, which comes from our phase, our two faces, our phase boundary on the surface. Right? Okay, so that's what we get. And well, we can first kind of simplify this. Or if you would only have one component, that goes back to what I discussed before. People have done this also just on a stationary surface, or well, it's well studied if there's no flow, then one has this two-component membranes, and in the overdamped limit of this, we also get this type of models. Okay, so it contains all these previously studied models, and now we can solve this as well. The standard way of doing this is to use some operator splitting, so solve this surface Canhilliard equation first on the old surface, let's say, then solve our Navier-Stokes equations with all our mesh regularization and so on, what we did, and then lift the solution to the new surface. And we again use this Taylor-Hood elements and so on. And indeed also for this more complicated or coupled system, get the expected order of convergence. Okay, so also here some entertaining movies. So that's we start with a sphere. So now there's no volume conservation anymore. We skip this for the moment. We start with something where we have already phase separated. We have these two different phases, so we look at the induced tangential flow and the phase or the coarsening of the system. So now it's strongly depending on the parameters what happens. Well, the surface can evolve, but also the interface kind of wants to reduce, and that can be done by kind of forming this bulks and reducing the interface by this. At some point that will lead to some pinch off. Our numerical method is not able to handle this, so we stop the simulation before that happens. So this is one mechanism which can happen. However, and if we vary the parameters, so the bending rigidity for the deformation of the surface well, goes down in this direction, so it's easier to deform the surface in that direction. Costs most energy in this configuration, and the Reynolds number goes down in that direction. So if it's very hard to deform the surface, then it essentially stays spherical or only slightly deforms, and you have all this coarsening mechanism of the interface between the two faces, leading to all this minimal configuration where the interface is now on this long axis on this. Yeah.
So if I understand correctly, we say here you have the same bending modulus for them. So the bending on the right hand side is really coming from reduction of the length of the interface.
Yeah. Right. So here we have some intermediate thing where we have coarsening of the faces and then leading to this this budding. And here, well, we essentially reduce the length of the interface just by this widening out, right? So that's the difference. I think this is understandable. But if you look at inertia effects, you don't see too much of a difference. However, if you look at the time where this pinch off would happen, then you see a drastic difference. So it changes by orders of magnitude. So kind of inertia enhances this this evolution around. Okay. Good. Also in this model, one can add active terms, and that's there is this active model H introduced by Mike Cates and others in 2D as an effective model to describe something like motility-induced phase separation and so on. If we use this methodology for our surface model, then it looks like this. So it's the model we have, and in the simplest setting, it's adding some active term which depends on the gradient of my phase field function. Okay. Now let's take a look what happens if we do this. So here now the bending rigidity is the same for two phases and also the spontaneous curvature and so on. And we start with something like this and let it evolve, and then well, we no longer have coarsening, well, domain splits and form and well, merge and so on. And this is all coupled to, well, the shape deformation and so on. And also this is very preliminary. It's just demonstrating that all their effects due to this activity as well. Okay, and that's essentially it. So well, what we studied is some highly nonlinear system of this surface PDEs with some complex coupling between the geometry and the PDE. In order to solve this numerically, some essential numerical features should be taken into account. So what one needs is some higher order surface approximation. So with linear or piecewise constant triangles or so, this simulation would not work. One would not get this convergence properties. Well, and this solid fluid duality leads to dynamic shape evolution, which are different from the classical models. And yeah, with this, I should mention the funding, so that's some research unit on this mathematical topic. And most of the simulations were done by Veit Krause, a PhD student, just submitted his thesis, and then Michael Nestler, postdoc in my group. And the derivation, essentially this Lagrange de Lambert principle, and the application of this was due to Ingo Nitschke, another PhD student. And then we collaborate within this research group with the group in Aachen from Arnold Reusgen. And well, quite recently we established this collaboration with Garrett and Sept. Thank you very much.
Yeah, so this is a very inviting question. How fast do these flows need to be to get an influence on the structures?
How fast?
Yeah, so that's what I mean. That's the fluid. Sorry, the flow, the velocity, the magnitude of the flow field. Does that somehow need to relate to the bending energy, or what's the what kind of sets the scale for what's the fast and what's the slow flow in terms of influence of shape?
Okay, so well, don't think that I really can answer this. So we only did this in non-dimensional units, and but I mean, that viscosity has some effect on in this biomembranes. I think this that should not be the question. I guess so. One you can measure this, and that's an issue. If kind of inertia really has an influence, okay, one can doubt this. This is of course highly viscous materials and so on. So. However, we like to solve the full Navier-Stokes problem and then use some very low Reynolds number. This even has numerical advantages of doing this way. But this is maybe an example where one could still argue that the viscosity is high in some extent, but it leads to different shape evolutions, right? So the dynamics is to some extent influenced. right? How relevant for like a specific membrane or so, this I can't answer.
So let's take the second row in the picture here. If I made if I just scaled it all up by a factor of 2, what would it to the required velocities?
This I don't know, but I mean, this is a logarithmic scale, right? So it really is on this plateau there for forever, right? Before something happens. So I would doubt that like just a factor of 2, even if this also the Reynolds number, if this would be the length scale or so, well, would not change this behavior too much.
Yeah, so the phase separation part at the end, I presume you were doing this with volume constraint?
Yes, I think this was no, that was not with volume constraint. That was yeah.
So you think that volume constraint would regularize the?
That will certainly regularize this a bit. Yeah.
And then also there's a question of scales. So with this active phase separation, there's kind of it doesn't continue coarsening, so there's a kind of preferred size for each of the droplets.
Yeah.
And you get to play with that relative to the overall size of the sphere that you're working with. Do you have any idea how these things work out? Where you get
no, we really just started this and added this, and that was the first like converging simulation.
I presume the example that you showed is in this reverse Ostwald Bergman regime.
Yes, right. It's the same regime where you get this behavior in 2D. Yeah. Yeah.
Yeah. Yeah, absolutely. Yeah. Have you got any examples where you've looked at flow either inside a saddle-type piece of surface or perhaps in a planar piece of surface, and then under the action of that flow it turns into a saddle-type surface?
Well, not on this from like a flat thing, but here, I mean, there's no flow at the beginning, right? So, yeah, so it's well, as long as you deform your surface by whatever force, then you induce flow. If your surface stays like it is, then you don't, right?
Yeah, so if I go to the second row again,
Yeah.
the shape on the far right, which is your terminal point.
This one, you mean? Oh, that one, right?
Yeah, yeah.
Yeah, that one is my, well, it's what we, well, you see that it's not 0, but it's very close to 0, the tangential velocity. We assume it goes to 0 and then the shape doesn't change.
But so the negatively curved parts of that, so the ones around the annulus,
Yeah.
Are they due to the elastic properties,
Right.
Of the bending modulus,
Right.
Or are they due to the flow?
No, they are due to the bending. Right.
Very beautiful work.
Thanks.
Is it clear? So if I'm saying with single phase active materials, you show 2 different initial conditions mean 2 different final states. Is it clear what the properties of your initial condition are which give rise to convoluted phase?
No, we have not explored this. So we just did this well within the last 2 weeks, and that's it. So it's not done systematically. What kind of phase diagram or what you would expect.
There could be other final states.
I mean, that's the, well, from this half-rich energy, I mean, that's two minimal states which are close in energy. I guess all the other states are probably at a higher energy.
Okay, thank you again.